Okay, well, good morning, everybody. If you remember, last time we were talking about the sort of potentials that you need to apply to protect your pipeline, and this was one of your last slides. If we put too much CP onto the system, then we're wasting energy, and we are also likely to delaminate the coatings, and we might actually get hydrogen embrittlement if we're not careful. So we don't want too much CP. On the other hand, if we don't put enough on, then we start getting pitting and defect development on the pipe. And one of the big problems is trying to get a uniform potential along the pipe. It's almost impossible. We're never working in ideal conditions, and you're bound to get some variation in potential along the length of the pipe. So some areas are perhaps better protected than others. And then you've got all the issues that we were talking about with straight currents, whether they're transient or permanent and so on. So the pipe potential is not only uneven along the pipe length, but it will also fluctuate a little bit due to external effects and changes in soil resistance and those sort of things. So we're finished with this slide, which shows you the comparison between the standard potentials for three different types of reference electrode. And I pointed out that although the copper sulfate electrode is used quite commonly for onshore pipes, that in seawater there's a tendency to use silver chloride, and that's about 50 millivolts different from the copper sulfate. And this goes back to something I said much earlier, and that is it's always a good idea to say what you're measuring your voltage against. So in this case versus the standard hydrogen electrode. So everybody is clear what potential you're quoting is. And you're about to see some values that are quoted for onshore and offshore structures, and you'll see the value of getting the potential quoted correctly. So you've had that scale, that's image before, so hopefully you've still got any files somewhere. Okay. So for onshore pipe, the ISO standard, which was came out in 2003, says that the pipe should be more negative than minus 850 millivolts and less negative than minus 1200 millivolts. And those values are versus the copper sulfate. So it should be minus 850 millivolts. And minus 1200 millivolts. It should lie between those two. So generally, as a general guideline, the potentials lie between -850 and -1200 millivolts versus the copper sulfate. And then they've added a few extra recommendations so that if you're in areas where there might be some microbially induced corrosion in anaerobic soils, then they recommend you should be more negative than -950, so somewhere between -950 and -1200. And then they further point out that if the temperature changes, then you may have to alter the potential range, and the recommendation is that anything above 40 centigrade you should start adjusting the voltages accordingly. And that's because the thermodynamics of the reactions change, because delta G is delta H minus T delta S. So if the temperature changes, delta G changes, and if delta G changes, then E changes, because if you remember the theory, because delta G equals minus NFE. So E changes. T changes, makes G change, makes E change. And then finally there's a footnote for the high alloy steels, stainless steels and so on, just to say that they start generating hydrogen much more readily than the ordinary API steels, so you have to change your potentials for them as well. So that's the recommended ranges for onshore. This is what is recommended for offshore. This is NORSOC, which is from 1997. And these potentials, you'll see, are a little bit different from these ones. And that's because NORSOC quotes them against the silver chloride. And if you recalled from just a minute ago, it's about 50 millivolts different. So it's saying the pipe should be more negative than -850 against copper sulfate, which is about -800 against silver chloride, and less negative than -1100 copper sulfate, which is 1050 silver chloride.
Does that mean that for stainless steel, the higher the prime number is, the more negative the potential must be?
You're going to see in a minute. it's actually the other way around, but you're going to see it in a minute. So these values, as quoted against the soda chloride, so the 50 millivolts offset from the previous onshore data that you saw for copper sulfate. And of course a lot of the offshore pipe is alloyed, and so there's recommendations for adjustment for your alloys. So quite often there's a 13% chromium steel. It's not a stainless in the true sense, in that it's not a chromium nickel alloy, but it is chromium rich, which makes it more corrosion resistant. And then there are the specific stainless steels themselves, the chromium nickel iron alloys. And they rate those in terms of their pitching resistance equivalence number, which is worked out by that formula there. So this pitching resistance equivalence is related primarily to the percentage of chromium, which may be about 10 to 25%. So you can see that this is going to be quite a big component of the PREN number. The nitrogen levels are somewhere between about 0.03 and 0.6%. So the impact of the nitrogen content is a minor fact in terms of the pitching retention number. But good morning. Okay.
Yeah.
Okay. So the sort of potentials that are recommended are considerably lower than those for ferritic pipe, and that's because it's much easier to start inducing cathode reactions on the surface, and of course the free corrosion potential of these stainless steels is very different from the free corrosion potential of ordinary ferritic pipe. So a lot of them are austenitic, that is to say they're face-centered cubic structures, stabilized face-centered cubic austenite because of the high nickel content, or they're duplex, that is to say they're a mixture of ferritic and austenitic phase. And that has some advantages because the two phases have slightly different properties, and so where you might get damage induced in one phase, it may not necessarily progress through into the other phase, and so you can stop the spread of attack because of the duplex structure. So it has some advantages. And now they've got hyper duplex and super duplex and so on. Sandvik making a lot of those. And then the nickel alloys, there's some high nickel alloys for marine applications in specialist areas. Obviously the costs are going up as you increase the alloy contents, and things like Manel are extremely corrosion resistant in the offshore effect. So the larger the PRN number, then the less CP you need, effectively. Okay. Right. This table's on your handout. You don't need all the details. The bit that I wanted you to pick out of it was that there were essentially three types of anode. Those that are consumable, those that are slowly consumable, semi-consumable, and those that are non-consumable. Okay, so three types of anode. And you pays your money and takes your choice, really. Depends on your application and how much maintenance you want to do. What you've also got, so the consumable ones are just cheap iron or cast iron, then silicon irons, which are a little bit more corrosion resistant, and then things like these coated platinized or titanium or tantalum or niobium coated steels, like the anode that I passed around in the class some time ago. There's a figure here. This is kilograms per amp year. Okay, so this is the rate of consumption of the anode material with time for a given current. Yeah, and you can see that the consumable anodes are getting used quite fast. About 9 kilograms are used for every amp for every year that the pipe is being protected. Whereas the semi-consumable, they drop down to about 1 kilogram per amp per year. So obviously the anode then is going to last almost, well, 9 times as long, almost 10 times as long. And then the non-consumable ones, the consumption rate is negligible. That's actually a typo. I don't know quite how that's happened. That should not read. It looks like amp meters per meter squared, but I'm pretty sure it's milliamps per meter squared. So, as I say, I don't expect you to recall all the details, but just to have a general feel that you've got consumable, semi-consumable and non-consumable electrodes. And the life of those electrodes obviously is scaled depending on their own corrosion resistance. Okay. On the other side of the handout, you've got this diagram, which is one of a pair that is intended to tell you something about what they call attenuation. In electrochemistry, they call it electrode throwing power. And basically, there's a fall off of the potential with distance because of the resistance. And if you've got a pipeline, which we've got here, with a connection point on it, and an anode some distance away from it, then you can plot the potential contours running from that anode through across to the pipe. And what you're aiming to do is to get the flattest, most even potential on your pipe. So the contour next to the pipe is relatively flat. That's rarely achievable. There are all sorts of things happening. It's a dynamic system. There's noise because of other things happening in the environment, and variation in the soil and so on. So this is an idealized situation. One thing that is marked on here, which is always worth thinking about, and that is the current flow in the pipe depends on where the connection point is. So you've got current flow going from across this way, and on the other side going the other way towards the drain point. As I say, in electrochemistry, they call it throwing power, and it's about the IR drop, essentially, in the environment. The other handout's got this slide on it, which is, again, an idealized attempt to illustrate what happens as you position anodes at certain distances along the pipe, typically about 10 kilometers or so. Yeah, 1 to 10 kilometers. This is a plot of potential against distance for this pipe with these two anodes located outside it. And what you've got is much better potential control near the anode and less potential control as you go away from the anode, and then the field of the second anode begins to interact and improve the potential control, and then the potential control falls off again. So trying to get an even potential along your pipe is not easy. And you'll get some areas that are well, you have to decide which way you're going to do. Do you want all your pipe protected and accept that some areas will be overprotected? And that's probably the best thing to do. Or you're going to go for none of the pipe's going to be overprotected, but some of it might be underprotected, which is probably not a good idea. So you've got to think about the average potential, if you like, along the pipe a bit. This is also on the handout. This is what they call a close interval potential survey. So between the test points that you've got spaced out along the sort of at 1 kilometre gaps along the pipe, you might want to start looking for defects over time, and that's what this gentleman's doing. What he's got is 2 ski sticks here, effectively, and each one of those has a reference electrode connected to it. And he's also got a couple of reels on the back of the carrier here, which allows him to connect to the test post. So you can start up at one test post and measure the potential on the ground, and to look at the instantaneous current off values. What he's also linked into with this device here is a timer. So he knows when the supply on the pipe is going to get switched off and when it's come back on again. So he can go to his next position, put his stakes in, the pulse occurs, power off, takes his readings, power on, goes to the next place, takes the next reading. So he's synchronized to switching on, switching off of the power onto the line. That allows him to generate this sort of data. And what we've got here is the, sorry it's in black and white on your handout, but the top line is the normal power on, and the pink line is the power off. And what you've got here on the blue curve are peaks, 1, 2, 3, and they are about 10 kilometers apart, and they're the supply posts. So they're not untypical of the system. Okay, you'll typically find this the potential of the supply posts is a bit more cathodic than in between the supply posts, like the festoon image on the previous handout. When you get the instantaneous current off, then you see the true potential on the pipe, and as you might expect, at the supply points where the current flow is the greatest, you get the greatest IR drop there, so you get the biggest difference in signal between the on and the off potential, because it's all due to Ohm's law and the I equals V over R. What there are here are some features. There's a spike here, there's a spike here, there's another one there, and they are possible defects in the pipe. It's possible because these potentials now are getting less cathodic, minus 600, this one's minus 400 or so. It's possible there's something happening there. Okay, so that'd be worth investigating a bit further. This sort of festoon arrangement of potential between the supply points isn't quite symmetrical here at this end, and that'll be some other feature in the environment. Perhaps there's a soil change. Okay, so real data has a lot more scatter in it, a lot more features in it. And if you want to look for defects rather than looking at average behaviour, this is the sort of thing you need to do. On the offshore situation, then obviously it's a bit more difficult, a bit more expensive, but there are a few things you can do. They have these, what they call towed fish arrangements, but essentially it's a trailing wire arrangement. So you're still electrically connected to your test point. There's a bit of cable going down to the fish, and that may have, it may also have a camera and things on it, but you're monitoring potential along the line in the same way as you do with the sticks on land. So camera and reference electrode, and the cabling to give you the connection to the structure, in this case an offshore oil platform. Another way of doing it are these ROVs, or remote operating vehicles. These are unmanned mini subs, really, mini submarines, and quite often have quite a lot of kit on them. This one's actually looking at a seabed line with anode bracelets on it. Okay, so at intervals there's a bracelet of probably aluminium zinc alloy or something like that. A bit more expensive again, of course. On a small scale, people do actually go down and use a device that allows them to puncture the coating and get a reading. So manual stabbings, and again, this is all with silver chloride reference electrodes because you're offshore. So that diver could do that. if the depth wasn't too much. Okay. So that's monitoring the pipe. I wanted to say a little bit more about isolation joints because we touched on them last time, and perhaps wanted to make it a little bit clearer. So it's easier to control sections of pipe, and you don't want potentials interfering with things like pumping stations and so on. So you tend to put insulation joints in. And straight currents are an issue because they create scatter in your potential monitoring data. And so sometimes you actually have to put a data logger on and record the average potential over a period of time to get a better feel for what's happening on your pipeline.
So excuse me, the first line of the previous slide, you need to insulate or to isolate?
Insulate is the same as isolate.
It's the same thing.
Yeah. Okay. So insulate is the electrical term. Isolate is a term just to say separate. Yeah. What you've got on your handout is this plot, which at first sight looks a bit complex. Sorry, again, it's black and white, so you might want to make some additions to it. So this green line is your current on. The blue line is the current off. The red line is your protection potential, minus 850 millivolts. So this is the protection potential you want. And you can see that at times, at certain distances from the test point, the potential is not cathodic enough. The pink diamonds are the results of what they call a DC voltage gradient test, which is one method for looking for defects in a pipe system. And essentially what it does is it looks for the potential gradient around the defect. And as you go past the defect, the gradient, the potential gradient, if you like, there's sort of a potential well round the defect, and so the gradient actually changes sign as you go from one side of it to the other side of it. The potential sort of curves down into the well, and it's a one method for looking for defects. And then there is actually some pit depth data. So this is actually a direct measure of the defects on the pipe. So what we've got here is a situation where when you go to instantaneous current off, it's clearly saying there isn't sufficient cathodic protection here, and that's verified by the number of pits and defects you find on the line at that distance from the test point. Again, here, and there's some pits, here, and there's some pits. What's interesting is that the voltage gradient measurement failed to find this set of defects. So you don't always, using only one technique can be a bit dangerous. You don't always get all the data. So, yeah.
I just beg your pardon for clarity on the pink and the red.
So the pink is the DCVG, and the red is the actual visual inspection. Is actually the direct inspection on the pipe. Okay. So. So the red are definite faults in the pipe. The pink are potential gradients suggesting that there might be a fault there. But the interesting thing is that they didn't pick up all the faults, so they missed these ones. But instantaneous current off did pick up this one, but failed to pick up these two. There is a little bit of a dip here, but it appears to be still above the cathodic protection limit. And this is part of the problem with taking the measurement at a particular time, because the soil resistivity changes with the seasons. There are other factors, stray currents and things, influencing the data. And so, in fact, what you want to do is surveys at a regular interval. So you can pick up what's really happening against the noise, against the seasonal variation and the interferences that are happening. Of course, there's no substitute for actually looking at the pipe itself, but that's not easily done if you're in a lot of situations, and not easily done with you don't want to just start disturbing or digging into coatings necessarily. Okay. So that's actual data. On the other side of that handout, you've got this little table of data, which tells you something about the standards for current demand. That's the current demand through the pipe in milliamps per square metre for particular design lines. And again, there's a temperature factor. You should make an allowance of 25% for every 10 degrees rise in temperature above 30. And that makes sense because the kinetics of the reactions are faster, the diffusion is faster, and so on. These abbreviations here, essentially we've got three types of coating. We've got plastics, so 3LPE stands for 3-layer polyethylene, and 3LPP is 3 layers of polypropylene. Okay, so we've got plastics, and then the next one up, where's the mouse gone? There it is, are the epoxies. So FBE stands for fusion bonded epoxy. Okay, and then liquid epoxy. So epoxy resins, which are really came in as a replacement for these more traditional coatings, the top list, which are the coal tar coatings. And unfortunately, coal tar is brilliant stuff, but environmentally, people are saying might be a bit of a pollutant, not so good. Maybe you should use epoxy. And sadly, you don't see, on old systems you find the coal tar, and sometimes it's a cold applied tape, and sometimes so that's what the tape reference is there. So you've got coal tars, which are the traditional original, epoxies, which really were aimed at trying to replace them, and the plastic coatings, which are usually multi-layer. And the current demand, of course, goes up over time because the number of defects goes up over time. Okay. This is some data which you don't need the details of, but I thought it was interesting to see it. And this relates to current demands for nominally bare steel in different environments. So the current demand is going to vary depending on where you are. And basically, as the conductivity and the salinity of the environment increases, then, which is roughly down the table, then the current demand goes up. So Maracaibo, which is in Venezuela, it's a brackish, it's a saltwater lake, and the current estimate is very high. Seawater pretty high, then fresh flowing water less and less, and then as you begin to run out of conductivity in groundwaters, then the current demand is quite small. Okay. This is one way of tackling the current demand. So you can do some calculations based on the design life, which may be 20, 25 years. You can think about how much of the coating is likely to be damaged over time. Okay, so next time is my last slot with you. I reckon it'll take about half an hour just to finish off this section. I'm going to talk a little, show you a couple of back of the envelope calculations connected with current demand and so on, and then that should round that off. So we'll probably end up having half an hour left at the end. If you've got anything that's been bugging you over the course of what I've been presenting, if you've got any questions, we can have a bit of a chat for the last half hour. I'll try and remember the answers. I can't remember the answers, I'll have to email you later on, but you know, if you want to have a bit of a look through, and if you've got things that don't make sense, then it'll be an opportunity to ask, and then my colleague will take over. Thank you. See you next week. Thank you. Cheers. Sorry? Well, I talked to the... Sorry. I spoke to the administrator and she said they were all there now. That's what she said.
Yesterday I checked.
I don't understand what's going on here. It was the 1314, wasn't it?
1314. So nothing there.
What I'll do is I'll photocopy it. So I don't understand what the admin's doing. They say that they can see they've got.
No, I checked yesterday.
Yeah. No, that's fine. That's fine. I'll make a copy.
Dr. Charles?
Yeah. Hello.
Yeah, I don't know, maybe you saw my email, sir. I sent you an email on Friday that I
Right.
will start doing about 2
Oh, I
weeks
saw that. Yeah, I
What do you think,
haven't.
sir?
Sometime during the Easter, you'll be able to get started. What I don't know is who's taking holiday when.
Okay, you mean
The technician and me. We haven't set our holidays yet.
No problem.
But yeah, I need to plan that. But certainly we'll be able to get started over the holiday. I'm not sure which weeks.
will be available? Yeah, I understand. No problem. When you confirm, let me know.
I'll get
sir.
you. Yeah, I will. I'll
thank you,
send
sir.
you an email. Thank you.
Thank you, sir.
And, you're welcome. Cheers now. See you, folks.
To be honest, I'm not worried about maintenance as long as they do their plans with work.
Damn, 4 hours. Shit. So what about something like maybe like 4